You ever stop and wonder what's telling a factory robot exactly what to do? Or, how a conveyor belt just knows when to stop? Well, there's this hidden brain behind it all, this piece of tech that's basically running our entire automated world. Today, we're going to pull back the curtain on that brain, the Programmable Logic Controller, or as you'll hear me call it, the PLC.
All right, so here's the game plan for the next few minutes. First, we'll figure out what this automation brain actually is. Then, we'll peek inside the control box to see its guts. After that, we'll get into the surprisingly simple language it speaks. And finally, we'll see how it actually senses the world and gets things done.
Okay, let's dive right into section 1, the automation brain. So what exactly is this thing?
I mean, really think about it for a second. An automatic drill. It's got to know exactly when to start and when to stop, right down to the millisecond. Or a packing system that's counting items and putting them in a box. None of that is random. It's all precision controlled. So the question is, by what?
And the answer? It's the PLC. You can think of it as a special kind of computer. But hey, don't picture the one sitting on your desk. This thing is built tough. It's made specifically for the rough and tumble world of the factory floor. So yeah, they're both computers, but they are worlds apart in what they do. Your PC, it's awesome for spreadsheets, for browsing the web. But stick it in a factory with all the vibrations, the heat, the dust? No way, it wouldn't last a day. A PLC, on the other hand, is built for that chaos. It's designed to live in that harsh environment, and it comes with all the right connections to hook straight up to massive heavy machinery.
All right, moving on to section 2, inside the control box. Let's pop the hood on this thing and see what really makes this rugged computer tick. So just like pretty much any computer out there, a PLC has 4 main parts. You've got the processor, or a CPU, the memory, the input-output system, we'll call it I/O, and of course, the power supply. Let's break down what each of these actually does.
Okay, first up is the CPU. This is the brain of the whole operation. Plain and simple. It's the decision maker. It grabs information from all the sensors, thinks about it based on the program we've given it, and then it decides what to do next. That's its whole job.
And where does it get its instructions? Well, that's the memory. Think of it like the CPU's personal notebook. This is where we write down the entire set of instructions, the control program, that tells the brain exactly how to make those decisions. It's the rulebook for the entire show.
Now, this next part is absolutely crucial, the I/O system. This is what gives the PLC its senses and its muscles. The inputs are the senses. They're the eyes and ears, letting the PLC see or feel what's going on out there. And the outputs? Those are the muscles. They're what let the PLC actually do something. Start a motor, open a valve, make things happen.
And last but not least, we've got the power supply. We can call this the heart of the system. It's just pumping out the electrical lifeblood that keeps the brain, the notebook, and all those senses and muscles working together. It might sound simple, but without it, nothing happens. It's absolutely essential.
Okay, section 3, programming with ladder logic. So we know what's inside the box now, but how do we actually write the instructions in its notebook? You're probably picturing lines of complex code, right? Well, you might be surprised by just how visual and honestly, how intuitive it really is.
To get why the PLC was such a game changer, you have to look at the old way. Before PLCs, if you wanted a switch to control a motor, you had to physically wire them together. Simple enough. But what if you wanted to change how it worked? Like, say, add a second switch that also had to be on. You'd have to get out your tools, cut wires, and physically rewire the whole thing. It was a massive pain, super inflexible, and took forever.
And this is the brilliant solution, ladder logic. So instead of dealing with actual physical wires, you use a diagram that looks just like those old electrical circuits. See the 2 vertical lines? That's your power. And each horizontal line, or rung, holds a piece of your logic. An input, like our switch, becomes a symbol called a contact. And an output, like our motor, becomes a coil. That's it. We've basically turned a messy web of physical wires into a clean, simple drawing on a screen.
But you might be asking, why this specific visual language? Well, this is where the genius comes in. As Thomas Hughes points out, the electricians and technicians back then, the people who would actually be using these things, already knew how to read these relay ladder diagrams. It was their native language. So by making the programming look familiar, they didn't have to go learn a bunch of complex computer code. They could literally adapt their existing skills, like, overnight.
Okay, section 4, sensing and doing. Let's bring this all together and connect it back to the real world.
We've got the components, we've got the program. Now let's see how a PLC actually uses its senses and muscles to get stuff done.
So, a PLC's whole job really boils down to two things: sensing and doing. The senses are its inputs, things like proximity switchers, photoelectric sensors, even a simple push button. They're what tell the PLC what's going on. And the actions? Those are the outputs: solenoid valves, motors, indicator lights. These are the things that physically make a change in the world.
Okay, let's look at a perfect example of an input. Picture a box moving down a conveyor belt. You've got a photoelectric sensor that's shooting a little beam of light across the belt. As soon as the box passes by, it breaks that beam. What happens then? The sensor sends a simple on signal to one of the PLC's input connections. Instantly, the PLC's brain knows one thing: a box is here.
So what happens next? Here's the action. Based on that ladder logic program we wrote, the PLC's brain says, okay, I see a box, my program says to push it off the belt. So it sends an on signal from one of its outputs over to a solenoid valve. That valve then opens up, releasing a burst of compressed air. That air moves a piston and, whoosh, the piston pushes the box exactly where it needs to go. See how that works? An input signal triggered a program decision, which caused a real physical output.
So when you step back and look at the whole picture, you really see the revolution here. PLCs took this rigid, inflexible world of hardwired relays and completely transformed it into flexible, changeable software. They put a tough-as-nails computer right on the factory floor that could be programmed by the same electricians who were already there. It was a total game changer.
The thing is, this technology is literally all around us, but it's designed to be invisible. So, here's a little something to think about. The next time you're in an automatic car wash, or you see a traffic light change perfectly on cue, or ride an elevator, just ask yourself, could there be an unseen brain, a PLC, quietly running the whole show? I'll bet you the answer is almost always yes.